Hi folks, so in this video we'll talk about the last or the third problem that we're trying to solve, and that is finding the square root of a given integer number, and let's assume it's a positive number. So let's again try to see if we can write the program with our pseudocode for this problem, if we can solve it. So the problem, let's say, find the square root of a given integer. This is the problem we're trying to solve. So the program starts again from the getting the input from the user. So we'll say int, and let's say the n is input. So we get user's input. This is the number, and we need to calculate or find the square root of this number. So one thing to know is whether this number is always a square or not, right? So if it's 9, 16, or it can be something that the square root of it won't be an integer, which is, it's not a square, basically. Let's say if it's 10, right, then there is no integer square root. So for now, let's assume it's any positive integer. We don't want to restrict it to only squares. And in that case, so once we have the input, what we should do, let's think of two ways. I think I briefly covered this also in one of the first introductory videos, but let's try to solve this using two different algorithms, right? One would be, if we don't know any formulas, we are far from math, we just know that the definition of square root, right? So we know that, again, we'll just put a comment, so this is not part of our program. So we know that if, let's say, if r is the root of n, let's type if r is the root or square root of n, then we know that r square is n, right? So r times r is n. So this is all we know, right? We all know this. We know only this, and we need to find r now and return as an output of this program. So let's think this way, right? So we can start, since we said n is always a positive integer, so it can be 1. The minimum input can be 1, right? The least number we can get is 1. The greatest one we can get is infinity. There is no limit. But we assume it fits in an integer, so we can calculate the maximum. We don't need it. But so if it's 1, what we can do is start from 1, right? So let's start from, let's assume r. So let's take r equals 1, right? And then what we do is just check if this expression is true, right? If we can say we cannot, basically we need to understand if the expression r times r is n evaluates to true, right? So if this evaluates to true, we need to return the output. So output r, right? So if this happens, we need to output r. If not, we need to say, so let's for now comment this, say check the value. And then if this is not true, we need to increment r, right? So either we can do the increment operator, or we can say r equals r plus 1, and then repeat the check. So the problem we have here is, again, we need to do that same thing many times, right? Until So in this case, it's a little different from what we had for the problem, the second problem where we need to count the number of boxes. So there we know exactly how many times to repeat, right? Because we know we have to count all the boxes. We have to go through all the boxes and check them. In this case, we don't know how many times we need to do. We just know that we need to do something until something happens, right? Until this condition is true, right? Or while this condition is false, we need to keep doing this. So these are different flavors of these repetitions, but we'll come to those. So, but again, we don't know how to do that now, so we cannot solve the problem. We cannot write a program to solve this problem with using this algorithm. So there is another algorithm, I think I mentioned this too. It's called the Herons method for calculating the square root. And let me just briefly explain what it does. So it's an approximation method, which means in every step you get a more precise answer, closer to the actual answer, square root, but you never hit the square root. So since remember that when we talked about floating point types, we said the precision is limited, it's not infinite. So if we write the program using floating point numbers, even though we don't hit the precise result, we will actually hit the result if we store it in a floating point data type, because that also is not precise. So there is some small epsilon number that will always be the error between the real value and what we can store, what we can represent in a single floating point data type variable. So the algorithm is basically this. So we assume we take some number between 1 and n as an approximation, and then there is this. So let's say, let me actually show you. So let me show you what I mean and how it works, this Heron's algorithm. So let's think of this. Let's assume this is the axis. This is 0. This is the n, which is our input, and we need to calculate the square root of this n. So let's assume this is the real square root, right? So r is here, and we need to find r. So what we do is we take an approximation somewhere between 0 and n, right? And let's say we take n, so half of n, right? Which is somewhere here. So, and we call this r0. So the Heron's method or algorithm is based on the observation that it's based on the observation that if r0 is to the right of r, so if it's greater than r, n divided by r0, so n divided by r0 will be less than r if r0 is greater than r. And the opposite is also true. So if r0 is less than r, then n divided by r0 will be greater than r. So this allows us to write this one. So the next approximation, in the next step, we take another approximation. We say r1. So we take, basically we divide n by r0, and in this case it will, let's say it will be somewhere here, right? Let's say it's somewhere here. So this is n divided by r0. So since these two numbers are always on different sides of R, we take the midpoint, right, of this sector. So we take this and we consider this the second approximation, R1. So R1 is basically 1 divided 2. Sorry, this is not very comfortable to write with the mouse. I'll type it later. So half of R0 plus n divided by R0. Okay, so yeah, it's not comfortable to type here. Let's go back to the notepad, but you get the idea, right? So in the next step, we take R1, we divide n by R1. So in this case, it will be somewhere here. Either, I don't know, yeah. And then R2 will be midpoint of this. So it will, eventually it will get as close as to R as we want. So the more we increase the number of steps, the closer we'll get to R. And that will eventually give a really good approximation. So let's say this is, let's call this simple method, and then let's call this one Herons method. Herons. So we take the same input, and then what we do is we say int R0 equals, and the approximation we start with n divided by 2. And then we say int, let's call it what? Endpoint, right? The other endpoint is R n divided by R0. And then what we say is R1 equals R0 plus endpoint divided by 2. So endpoint doesn't make much sense because we don't know which one it is. So we can get rid of this and just inline this expression. So we say n divided by R0. Right, so in second step, so R1 is a better approximation than R0, but we don't know how close it is to the actual solution. So we can do R2 equals R1 plus n divided by R1 divided by 2. Again, right, we can do this how many times? That's the question. How many times should we do this, right? So one approach is just do that. Do benchmarking, or heuristically we can see that like after 10 times it's really close. So one way is do that 10 times and then just return or output R10. And this will be really close to the actual number. It won't be the same result. So we'll talk about that, what we should do with it. But this is one approach, right? Do it 10 times. But what if it's good enough after 3 times? What if we don't need this precision? So another approach is to get the error, right? Like the calculation error as input. So we'll input, we can say get the number plus get some epsilon, which is the error, the acceptable error. So input, and acceptable error means that the result, the answer we provide, is different from the real answer, the precise answer, by at most this much, right? So we can calculate this. But in this case, again, how do we know what's the precise answer to take the difference and compare with epsilon? So there are methods to do this, but this is one way. You get the error as an input, right? Another way is actually, let's keep it here. So one way to check this, right, is before returning, we can say Okay, let's say we calculated this, so it would be actually R9 plus n divided by R9 half. Okay, so one way would be just to prove that it's close enough. We can say R10 by R10 minus n, right? So the square of R10 and the difference between square of R10 and n, which is the actual square, is less than epsilon, right? So if this is the error of the answer, not the square of the answer, it should be epsilon square, really. Then we can say, yeah, this answer is good enough. It's precise enough for this call, and then we just output. Again, we don't have. So one way is do this 10 times or do this 100 times. Again, this the same problem here as in the previous two example problems. So we need to do this the same step until we hit a condition, right? So we need to do the same thing again and again until this condition is true, right? So if this condition, the value of this expression is true, then it's a good enough precision, we can return. If not, we should continue. So this is another way. So if we consider, can we actually write the code? We cannot write this because we don't know how to repeat this same thing. We cannot write this code because, again, we don't know how to repeat, right? So again, we are missing. So as we saw from all the three problems, we need this. We need some way, some structure or some mechanism to do the same thing again and again. That's one thing we need. And the second thing we need is to check for conditions, right? Is this happening? If this is true, do something, else do something, right? We have some form of it, which is the ternary operator, where we can say evaluate this expression, evaluate that, but that doesn't provide the freedom to just say, if this happens, do whatever we want, right? It just gives you a way to evaluate two expressions of the same type, but you don't have the freedom to write whatever you want if the expression is true, something unrelated if the expression is false. So those are the two big missing things, and in the next video we'll cover control flow statements, which are the things actually we need, and we'll get to all the details. So let's go to the next video and learn about control flow statements.